morning, all of you. We'll start the class with a how do you feel? Let there be that at least that feel for you. Okay. So in the last class, we were discussing about Faraday's laws of electromagnetic induction as well as Lenz's law, and you all know that by Faraday's laws of electromagnetic induction, there are two laws. The first law gives you the phenomenon. What is electromagnetic induction? So, and the second law gives you what is the magnitude of electromagnetic induction. Lenz's law states what is it if by electromagnetic induction an induced EMF is produced. If so, the induced current will flow in which direction? So as I told you, Lenz's law is not a quantitative law. It just gives you the idea of what is the direction of induced current. And it is like a human natured law in the sense that we all would like to have no change. We are comfortable in our zones, or we do have comfortable zones, and so we don't want to change. Lenz's law exactly says that. Okay. Now I'm going on directly on to a problem. Please write down this problem. A coil of 200 turns, a coil of 200 turns is wound on a magnetic circuit, of reluctance 2000 ampere turns per Weber, of reluctance 2000, unit of reluctance is ampere turns per Weber. If a current of 1 ampere, flowing in the coil is reversed, direction is reversed, changed, okay, is reversed in 10 milliseconds. Find the average EMF induced in the coil. The average EMF induced in the coil. Okay. No, I did the wrong one. Yeah. So can you see my whiteboard here? Devanand?
Yes, ma'am.
Okay. Oh. So I'll just read out the question once again. A coil of 200 turns, which means N is equal to 200. A wire is wound on a magnetic circuit whose reluctance is given by 2000 ampere turns per Weber. If a current of 1 ampere is reversed in the coil, or flowing in the coil is reversed in 10 milliseconds, you are asked to find out the induced EMF. E, as you know, by Faraday's laws of electromagnetic induction, is minus N d phi by dt, which is the same as I told you, minus d psi by dt, where psi is the flux linkage. Flux linkage means it includes the number of turns also. So for this problem, let us forget about this minus sign. Okay, we are not concerned about the direction of the induced current. Now, in this equation, we are asked to find out E. We know the value of N. We know what is dt. The only unknown is phi, which can be found out given the reluctance, etc. So what is the equation governing, or equation relating flux and MMF and reluctance? Flux phi, which we have already learned. Flux phi is equal to MMF by reluctance, or phi is equal to MMF is ampere turns, Ni by S. Here N is given as 200 turns. Current is given as 1 ampere into 1 divided by S is given as 2000, or fluxes will be obtained as 0.1 Weber. Now you can directly apply this to this equation. You will get E is equal to N d phi by dt is equal to 200 into d by dt of phi. What is the change in d phi? D phi. What is d phi? Change in flux. That is, current was passing in one direction. 1 ampere was passing in one direction for 10 milliseconds, and then it was reversed. After 10 milliseconds, it was reversed. Current was originally flowing from, say, from left to right. After 10 milliseconds, it was reversed, which means this flux also gets reversed. Or d phi will not be 0.1, d phi will be 0.1 minus 0.1. This is the small catch here. Always remember, whenever there is a change in direction of current, flux also, magnetic flux produced by that also changes. So d phi is not 0.1. D phi is 0.1 minus 0.1, that is 0.2 amperes. So you substitute it here, 200 into 0.2 divided by every 10 milliseconds. So 10 into 10 raised to minus 3 to make it seconds. Okay, and you will get it as 4000 volt. This is the EMF induced when a current of 1 ampere flows through a coil of 200 turns, and that is getting reversed every 10 milliseconds. The induced EMF will be 4000 volt. Is this clear?
Yes, ma'am.
Yeah. The only thing that you have to remember is don't go wrong here. This is a very simple problem, but don't go wrong in this part. Okay. So I'm just rubbing off. I'm deleting this. Okay. Then we'll come back to Faraday's induced EMF phenomenon. Induced EMF. Now, in order to induce an EMF in the coil, three things are required. One, magnetic field. Two, a conductor or a coil. Conductor or a coil. And the third most important thing is that the magnetic field should be the magnetic field should be varying. It should be varying. These are the three things needed for an induced EMF to happen, or for an EMF to be induced. So you have to have a magnetic field, you have to have a conductor or a coil in which an induced EMF is to be produced. And that can be produced only if magnetic field is varying. Or our Faraday is not interested, this is very important, not interested in how much flux is there, how much magnetic flux is there or is present. What is he interested? He is interested, extremely interested. He is interested only on how flux is varying. Let there be a little amount of flux also. He is not interested whether there you have a large amount of flux or whether you have a small amount of flux. What he is interested in is to check how flux is varying. So what we can do, or what we can do to make him happy, is that Mr. Faraday, we can vary the field in two ways. Where you can bring in the change in magnetic flux in two ways. You can have a conductor, you can have a magnetic field, and you can rotate the conductor. So that when you rotate the conductor, the magnetic field or magnetic flux is being cut, and then an induced EMF can be produced. And that EMF is called as a statically induced EMF. Statically induced EMF. And Faraday, we can also do something. You can have a conductor, you can have a magnetic field, and you can vary the magnetic field. Vary the magnetic field. When you vary the magnetic field, you call it as dynamically, sorry. One second. When the conductor, this is dynamic, sorry. Oh God. When you rotate the conductor, when the conductor is moving, you call it as a again doing the same. Okay. When the conductor is being rotated, you call it as a Dynamically induced EMF. Dynamically induced EMF. When the conductor remains stationary and the magnetic field is varying, whatever be the way in which it is varying, you call it as a statically induced EMF. Induced. Okay, so Faraday would be happy when you have a conductor, when you have a magnetic field, and when you cause some method by which the flux is varying. If you can cause the flux to vary, then EMF will be induced in it. Now, how can you make the flux to vary? One thing is to have a conductor like this, and can you see my conductor? Anyone? This is my conductor. Can have a conductor. You can have the magnetic field like this, and you can rotate. Then you will have a north pole here, you will have a south pole at the bottom, and you can make the conductor rotate within the magnetic field, which means at this point, when it is getting rotated, during the rotation, the magnetic flux lines are getting cut, and as a result of which an EMF will be induced in it. Okay. So that is called as dynamically induced EMF. So that is being practiced. You keep the conductor stationary and the magnetic field is rotated. This is how in a generating station alternator works. Or a AC generator. Now, Riddicky power station, what we do is we have a magnetic field and the conductors are there. The conductors are rotating within the magnet, or this is the conductor is remaining, his conductor is getting rotated. So this is, today everything is getting, this should not happen to me, no, should not have. So you have a conductor, the conductor is rotating within a magnetic field, and you have a DC generator, where the conductor or the armature is rotating within the magnetic field. And then you can even have a condition where the conductor is rotating. So the conductor is stationary and the magnetic field is rotating. Magnetic field is rotating. That is where this is being applied in an AC generator or an alternator. AC generator in our Riddicky power station. Anyway, whatever is done, what we do is you have a conductor, you have a magnetic field, and some relative motion is there, or some way in which there is a change in magnetic field. Now the question is, can we bring in another case where you have a conductor, you have a magnetic field, there will be a motion, whether the conductor moves or the magnet moves. You can bring in induced EMF. Suppose there is a condition where neither the conductor nor the magnetic field is physically moving. Instead, the magnetic flux can be varied even if you give a AC current as the electromagnet. So that is what is happening in a transformer. Now, in an AC transformer, in a transformer, there are no moving parts. Yet there is a conductor, there is a magnetic field, and this magnetic field is varying. How do you make the magnetic field vary? By passing an AC current, which is AC means alternating current, which is going on changing its value instantaneously. When the current goes on changing its value, the magnetic field also goes on varying. So Mr. Faraday is now happy. So you have dynamically induced EMF as well as statically induced EMF. Now, I had gone a little wrong while I was writing it. Just remember, when the conductor remains stationary, it is statically induced EMF. And when the conductor rotates, or when the conductor is dynamic, it is dynamically induced EMF. It is dependent on the conductor. Conductor rotates or conductor changes position means dynamically induced. Conductor remains static or stationary means it is statically induced EMF. I hope that much is clear to you. And then there is an equation for, so today we will be looking into dynamically induced EMF alone. We'll be discussing a little bit about dynamically induced EMF alone, where you have a conductor moving in a static magnetic field. Okay. So I'm very sure all of you have learned this equation. I'm not going very deep into the derivation, dynamically induced EMF. Okay, which means you have a north pole, you have a south pole, and naturally there will be flux lines like this or field lines. These are not actually lines, but these are imaginary lines that we assume so as to perceive what is magnetic field, and most of the phenomena are easily described by this. So that is why we say you have flux lines. It is not that there are actual flux lines there. This assumption of flux lines help us to perceive almost all the phenomena that is possible. So that is there. All those can be explained clearly. So we have something known as field lines for our explanation sake. And suppose there is a conductor. This is a conductor. I'm just showing the cross section of the conductor, which may be moving with a velocity v. Making an angle V like this, so that with this is theta. So it has a component V cos theta, velocity V meter per second. Okay. And then this is V sin theta. You all know. Let this flux be of B Tesla. And let the length of this conductor, let it be. These derivations may not be required even, but just to make sure that you remember, let that be L. And then the flux cut. When does the flux be? How is the flux cut? Because the conductor is within the magnetic field. The conductor is moving with the velocity. So the flux cut will be flux density B into area swept, isn't it? Area swept by this conductor. What will be the area swept? B into the length of the conductor, this length. I have shown only the cross section. This is the length. This is the conductor which is moving like this. So the length of the conductor, L, and the distance through which it moved. Let the distance that it moved be dx. That is, dx is the distance moved in a time dt by a coil or by a conductor of length L. Conductor of length L moving a small distance dx with a velocity v in small time dt. Okay. So this is your flux cut. Now, E is equal to N d phi by dt. This is phi. Okay. So that is equal to, let N, for easiness sake, I am taking N is equal to 1. If so, E is equal to, again, I have left that negative sign also. I am not bothered about the direction now. So that will be d by dt of B L dx by dt. Now the only catch here is that I should not consider V. Instead, I should consider V sine theta component, because I am concerned with that component of velocity which is exactly perpendicular to the flux lines. So here d, which means dx by dt, when I do that, this dt goes in, so I can safely put this like this, and I'll get B L V, this dx by dt in the perpendicular direction will be V sine theta. Had this conductor been moving exactly in the perpendicular direction with the velocity v, it would have been just BLV. Now, because it moves with in another direction, theta, so you have BLV sine theta. There is nothing new in it, I know. That is why I am not going to explain much about it. But the equation for dynamically induced EMF E is equal to minus d psi by dt is the same as BLV sine theta, where what is V? Velocity. Okay, so that is one equation that you have to remember. Let me directly come to another problem. Please take down. This is very important. The problem is very easy, but when you perceive what is happening, it is very important. An aircraft. I am speaking about an aircraft. An aircraft has a wingspan of 56 meters. An aircraft has a wingspan of 56 meters. It is flying horizontally. At a speed of 810 kilometers per hour. 810 kilometers per hour. And the vertical component of Earth's magnetic field. Vertical component of Earth's magnetic field is 4 into 10 raised to minus 4 Weber per meter square. That is Tesla. Calculate the potential difference. Calculate the potential difference. The wing tips. Potential difference between the wing tips of the aircraft. Wing tips of the aircraft. I'll read the question once again. The aircraft has a wingspan of 56 meters. That is, L is equal to 56 meters. It is flying horizontally at a speed of 810 kilometers per hour. Means velocity is 810 into 10 raised to minus 3. So 10 raised to 3, 10 raised to minus 3, 10 raised to 3 divided by 3600, which as per calculation you'll get as 225 meter per second. Okay. And the Earth's magnetic field is given as B. Vertical component of Earth's magnetic field is given as 4 into 10 raised to minus 4 meter per second. Weber per meter square. Calculate the potential difference. Today all my concentration has been gone because of a certain environmental problem here. Okay. Sorry for the inconvenience. But again, whatever mistakes I have made the correction then and there. Okay. Now, this is equivalent to aircraft now is a conductor, which is moving in the Earth's magnetic field. Now, Earth's magnetic field vertical component is given means theta here is 90 degrees. So, you needn't worry about the other things. So, here it is a case of dynamically induced EMF. This actually happens in aircraft because when the aircraft is moving in Earth's magnetic field, actually potential difference is coming in between the wing tips of the aircraft, and induced current can also flow. So certain safety precautions have been taken in the aircraft by the designers themselves. All these calculations, though this equation seems to be a very trivial small equation, this equation is something that that has been useful in every aspect of human life, even in aircraft. So here what is E? E is induced EMF, dynamically induced EMF, given by equation BLV sine theta. Theta is equal to 90 degrees. So you just have to put in all the values, substitute all the values, 4 into 10 raised to minus 4. I hope you understood why I took it as 90 degrees, because they have already given you the vertical component and the aircraft is moving horizontally. So the 90 degree component itself has been given. 4 into 10 raised to minus 4. L, length is the length of the wingspan is given as 56. It is moving with a velocity of 225 into sine 90. That is 1. So you are getting 5.04. This is the dynamically induced EMF in the aircraft. So let me just put this, I have to, yeah, 11:30. So it said that after 30 minutes, students are getting stressed. So I may have to stop here. Okay. Before stopping, let me. I know today you might not have gathered anything much more than whatever you have learned in +1, +2 classes. Yet I think you could appreciate at least some of the things that has come in. Always remember, had not been for Faraday, like Faraday was asked by one of the reporters, Faraday, what is this, what you have rotated some conductor within a magnetic field and produced something that you call as dynamically induced EMF, a little bit of electricity. So what is that? What, at that point in time, what significance does it have? Why is it called? So his answer was, someday a day will come when you will be able to tax this thing. Now you know how much electricity charges that we are giving. Now you know how much of tax we are paying on this particular thing. So he was a visionary. The reporters didn't have that kind of a vision. So that is life for us, dear students. No, visionaries have contributed a lot to the comfort and improvement of mankind. Let us appreciate that and stop for today. Tomorrow I'll come up with statically induced EMF as well as something known as magnetic damping. That is not included in your syllabus, but I just want to mention something about that also. And thank goodness that the whole phenomena of electromagnetic induction is obeying Lenz's law. In one way, if you look at it, Faraday and scientist Lenz, they were opposing characters. They were, enemies. Faraday wanted the flux to change. Lenz has always wanted the flux not to change. The current was flowing in such a way that the flux should not change. So Faradayയും ലെൻസും ഒരു enemy എന്ന് പറയണ്ട, അവർ enemy പോലെയുള്ള phenomenon ആണ് പറഞ്ഞത്. So thank you for today.